This tutorial is on how to determine if a covalently bonded molecule is polar or not. And it's just a quick walkthrough of how our simple decision tree process to understand how this is without doing a lot of drawings and all that types of materials. So if you can follow the decision tree process with these 4 easy steps, you should be able to determine any molecule, whether it's polar or not, if it has covalent bonding. So here's the decision tree for making a decision between polar or nonpolar on a molecule. Now you first have to understand a couple of things before we use this decision tree. One is you need to understand the VSEPR rules and how to draw Lewis structures. And if you don't know how to do that, then you should spend some time learning how to do that before you tackle this tutorial. And the other thing is you need to understand what electronegativity is of an atom and how to determine the difference between two atoms in a bond. So if you can do that, then this decision tree is pretty self-explanatory of how to make the process. So let's just quickly start on the left-hand side of the chart here, and we're going to ask what is the molecule, and you're going to draw. You would draw your molecule, let's say here, to help you out for the starting of it. You're going to draw your molecule here, and you can either draw it using the Lewis dot structure, or you can draw it using the VSEPR rules to help you move on. And then you're going to ask the first question, is the molecule a pure hydrocarbon? So it just contains carbon and hydrogen atoms only. And if it does, then it's a nonpolar molecule. No matter how many carbons and atoms around there, there's not enough difference in electronegativity between the bonds. The bonds are all nonpolar, therefore there can't be a polar side or not. So the answer would be yes, and it's nonpolar, and you could stop there. The next question you would have to ask, if it's not, if there are other atoms besides carbon and hydrogen, is the shape symmetric? So we're looking at symmetric shapes of being tetrahedral, octahedral, trigonal planar, linear, and the other ones that may not be mentioned here that could be considered symmetrical. So symmetrical means that everything looks the same on each side, right? A four-sided triangle, linear, no matter which, basically it has to have axis of symmetry. So if it's not, if the molecule is another thing besides one of those symmetric shapes, then the molecule is polar, right? Even if it's slightly polar, it's still polar, right? So for example, a trigonal pyramid would be a polar molecule. And then the last one is, if it is, yes, the molecule still may be nonpolar, but it's going to be, we have to do another decision process to make sure that we understand whether or not it's polar or not. And again, you're going to need to use VSEPR rules and Lewis structures to determine the shape, whether or not it's symmetric or not. And the next decision point is, are there polar bonds in the molecule? Well, typically, if you're going to have a asymmetrical shape, there's going to be some type of polar bonds in the molecule. So the answer pretty much is going to be yes on this one. There may be a few exceptions where it's no. So that's why I've included it here. And to determine whether or not a bond is polar or not, you're going to use the electronegativity difference between the two atoms involved in the bond. So if the electronegativity difference is, remember, if the electronegativity difference is going to be greater than, let's say, 0.02, if the electronegativity is greater than, let me do it the proper way. If your electronegativity difference is greater than 0.2, that's the electronegativity difference, then you can consider that a polar bond. And this value here was somewhat arbitrary. Some people say it's 0.3, some people say it's 0.4. But for this particular discussion, if it's 0.2 or more, it's going to be considered a polar bond. If it's more than 2.0, then you no longer have a covalent bond, you have an ionic bond. Or there will be an ionic bond character to the bond. Whether or not that's full ionic bond, there's some other rules that have to be applied. And we would do that when we understand what the difference between a covalent and an ionic bond is. But generally, if it's between 0.2 and let's say 2, then you're going to have a polar bond. And the last thing we need to understand is, are all the polar bonds the same? So if all the bonds are polar, yet they're all the same end molecules, so for example, in, let's say, carbon tetrachloride, those bonds are polar, It's a tetrahedral, but their bonds are polar, but they're all the same. So all four of the bonds are a carbon-chlorine bond. Therefore, the molecule is going to be symmetric and the polarity of the entire molecule as itself is going to be nonpolar, even though there are polar bonds involved. So if all the polar bonds are the same, then the material is going to be nonpolar. If one or more of the bonds are different than the other ones, then there is going to be a polarity system. All right, so that should be pretty easy to understand when you look at. So let's look at some examples on this real quick on the other page. Okay, so I drew the Lewis structures for all the compounds listed on the page, and let's quickly go through the rules as we mentioned on the other page to see if we can determine whether or not these are going to be polar molecules. So the first one is does the molecule contain only carbon and hydrogen? So the answer to the first question is going to be no for this one. So we're going to put no here. And then the next question is does the molecule have symmetric shape? And yes, it does, because it's a tetrahedral. Although it's a little bit of a lopsided tetrahedral, but it's still a tetrahedral. And then the second question is, does it contain polar bonds? Yes, it does. It contains 3 polar bonds. Here's 1, here's 2, here's this one is not a polar bond. This is 3. So it contains 3 out of the 4 polar bonds. And since it contains, and then the last question is, are all the polar bonds the same? And the question is no, because we have a bond that's not polar, and therefore this molecule is going to be polar. So this is going to be polar, all right, and that's going to be polar. And then the next one is carbon tetrachloride, and so we're going to look at that one. First question is going to be guess no. It doesn't contain both a carbon and hydrogen, so that's no. And then the next question again is going to be the same one. Is it symmetric? And it is symmetric. It's a tetrahedral. So we're going to write yes there. And then the next question is, does it contain polar bonds? And it does. The carbon and chlorine are going to be a polar bond. And then the last question is, are all the polar bonds the same? And the answer is yes. So this is going to be nonpolar. Even though it has polar bonds, it's nonpolar because all the bonds are the same. They're all pulling in the correct direction. The next one is H2O, so we already know that that's going to be no for the first question. Is the compound symmetric? The answer to that is no, because if you do the correct Vesper and Lewis structure for this, you're going to see it's bent. So therefore, it's going to be polar. So you don't have to go any further than that, right? It's polar. And then the next one is nitrogen. Nitrogen is a non-carbon hydrogen material, so the answer to that one is going to be no, it doesn't just contain that. And then the next question is, does it contain, is it symmetric? It is symmetric, so therefore it could be non-polar. And the next question is, does it contain a polar bond? And the answer is no, so it's a non-polar material. Non-polar. And then let's look at ammonia. Ammonia has not both carbon and hydrogen, so it's not a pure hydrocarbon. So the answer to that one is no. Is it a symmetric system? The answer to that is no. It's a trigonal pyramid, so it is a polar molecule. The next question is for the next one, carbon dioxide, and so does contains both carbon and hydrogen? No. So we already made that one. And then is it symmetric? It is symmetric, right? Does it contain polar bonds? It does. And are both polar bonds the same? They are. So this is going to be nonpolar. So just because it's polar bonds, remember this polar bond here is pulling just as much as this polar bond here, so the net effect is 0. So let's look at hydrogen chloride real quick. Hydrogen chloride, we already know it doesn't contain hydrogen and carbon only, so the answer to that one is no. The answer to that one is no, and so we're going to put no there. And is it symmetrical? Does it have a symmetrical shape? Well, it's got a linear shape, so it's by definition doesn't really have a shape. It's just one bond, and therefore, we just got to look now to see if that bond is polar. And so the answer is yes. We know it's polar. So the answer to this is going to be a polar molecule. We don't have to go through the whole decision tree for that one. It only contains one bond. And there's no real central atom. So by definition, if the bond is polar and there's only one bond, the molecule is polar. And then the next one is HCN. We already know the answer to the first question is going to be a no to the, is it only carbon and hydrogen? And the second question is it linear? Yes, it's linear, and that implies that it could be, well, linear, it says that it has it is a symmetrical shape. All right. But the next question is, does the linear molecule contain polar bonds? And it does. We know that this bond here is polar. If you do the math real quick, the electronegativity of carbon is 2.5, the electronegativity of nitrogen is 3, and so the difference there is 0.5. And if you do it for hydrogen and carbon, the difference is 0.3, which is considered to be a nonpolar bond. And therefore, there has a polar end to this molecule, and therefore, it's going to be a polar molecule. Right, and you can look at it too. It's just from symmetric point of view. If you drew a line right down the carbon here and looked on both sides of this, they're not the same. So therefore, it's got to have some type of polarity. So this is going to be polar. And then the last one is formaldehyde, H2CO. And you can kind of look at this already and say, well, that's going to probably be polar, but let's go through the rules. It doesn't contain both carbon and hydrogen only, so the answer to that is no. Is it a symmetrical shape? Yes, it is. It's trigonal pyramid, trigonal planar, so that's yes. Does it contain polar bonds? It does. Are all the bonds polar? They're not. So here's our only polar bond here, right? That we considered this one to be a non-polar bond. So here's our only polar bond. And so one out of the 3 bonds in the plane is going to be polar. Therefore, the whole molecule is going to be polar. So hopefully that helps you. If you still are confused, you should come find me.